Hello everyone, my name is Dr. H.S. Madhusudan, Assistant Professor of Mathematics. This is a BSc program of University of Mysore, Mathematics, 3rd semester. Title of the paper is Algebra 2 and Differential Equation. And this is session number 18. Okay, in the previous session, we have proved many theorems on normal subgroups, and we know that normal subgroups plays very important role in groups. Now in this session, let us solve some problems on normal subgroups. So first problem is, let H and K be two normal subgroups of a group G such that H intersection K is a set consisting of only one element E. Then show that Hk is equal to K into H for all H belongs to H and K belongs to K. We know that if H and K are two subgroups of a group G, then H intersection K is also a subgroup. Okay, so subgroup must contain the identity element. So here E is identity element. Okay, now proof. Let H belongs to H and K belongs to K. We are taking arbitrary elements belonging to capital H and capital K. Now we have to show that Hk is equal to Kh, right? The idea here is to show that H, K, H inverse, K inverse belongs to H intersection K, which is set consisting of only one element, identity element. Now this implies H, K, H inverse, K inverse will be equal to E, and when we multiply both sides on the right by E, K, we get H, K, H inverse, K inverse into K equal to E into K, right? Now we can multiply K inverse into K and we get identity element. So therefore we have H, K, H inverse into E equal to K. Now Hk, H inverse into E is nothing but H, K, H inverse, which is equal to K. Now again multiply H both sides on the right hand side. So we have H, K, H inverse into H equal to K into H. Now H inverse into H is identity element. So H, K is equal to KH. So that's all. So we have to show that L, H, K, H inverse, K inverse belongs to H intersection K. Now H is normal in G and H belongs to capital H, implies H inverse also belongs to capital H. Now H is normal in G means G, H, G inverse belongs to H for all G, H inverse, G inverse belongs to H for all G belonging to capital G. Now, since K belongs to K and K is contained in G, so we can replace this G by K, this K, and this one, this K. So therefore, K into H inverse into K inverse belongs to what? H. Now, H belongs to also, H belongs to what? H. Therefore, H K, H inverse into K inverse belongs to H, right? So this is one. Now, K is normal in G. Therefore, K is normal in G. Therefore, H K H inverse belongs to K. Because H belongs to H, which is contained in G. Also, K inverse belongs to capital K because K is a subgroup of G. So therefore, K itself is a group. So whenever K belongs to K, K inverse also belongs to K. Now, therefore, H K H inverse into K inverse belongs to K. See, because this element belongs to K and K inverse also belongs to K. By closure property, HK H inverse into K inverse belongs to capital K. So this is true. Now we showed that HK H inverse K inverse belongs to H, and here also HK H inverse K inverse belongs to K. Hence, H K H inverse K inverse belongs to H intersection K. So, we showed that HK H inverse K inverse belongs to H intersection K. This implies HK is equal to KH. And this is true for all H belongs to capital H and K belongs to capital K. Okay, let us solve the second problem. Let H be a subgroup of a group G and x square belongs to H for all x belongs to G. Then show that H is normal in G. Okay, proof. See, here x square belongs to H means what? This implies x into x belongs to H. Here dot means binary operation of G. So instead of writing star, we usually write dot, right? So this is nothing but x star x belongs to H, which we denote by x square. That's all. Okay. Now H is to prove what we need to prove. To prove H is normal in G, that is G inverse belongs to H for all G belonging to capital G and H belonging to capital H, right? So to show that G inverse belongs to H for all G belongs to G and H belongs to H. So let us take arbitrary element G belonging to capital G and H belongs to capital H. So let G belongs to capital G and H belongs to capital H. Now here the idea is we show that G into H whole square belongs to H, comma, H inverse belongs to capital H and G to the power of minus 2 belongs to H. And when we multiply these three, that belongs to H, and that we can show that product is G inverse. That's all. Okay. Now, since G belongs to G and H belongs to H and G is a group, what we can write is G H belongs to capital G, right? Because G is a group. Now G H belongs to G and therefore G H whole square belongs to G. Why? Because it is given that for all x belonging to G, x square belongs to H. This GH square belongs to H. This belongs to H. Now since H belongs to capital H, implies H inverse definitely belongs to capital H because H itself is a group. Now G belongs to G implies G inverse belongs to G. So this implies G inverse power 2 belongs to H. And this is nothing but what? G inverse dot G inverse. So we can write this as G power minus 2 belongs to H. So therefore GH whole square belongs to H. H inverse belongs to H and G power minus 2 belongs to H. So therefore, since H is a group, by closure property we have GH whole square into H inverse into G power minus 2 belongs to H. So now GH whole square means what? This is nothing but G into H into G into H, GH into GH into H inverse into this is nothing but G inverse into G inverse. This belongs to H. So this implies now we can combine these two because associative property holds. So therefore this is GHG into H inverse into G inverse into G inverse. This belongs to H. So this implies G H G and this is what? E. So we can remove that. So we have G inverse into G inverse belongs to H. Now when we combine these two, this gives what? G H E G inverse belongs to H. But E into G inverse is nothing but G inverse only. So this implies G H G inverse belongs to capital H. So therefore H is normal in G. Okay. Now problem number 3. If H is the only subgroup of finite order M in the group G, then show that H is normal in G. Proof. Given order of H is equal to M, and this is the only subgroup of G having M elements. Now we show that X H X inverse is equal to H for all X belongs to G. So this implies H is normal in G. So let X belongs to G and consider X H X inverse, which is equal to set of all elements consisting of X small h X inverse, such that H belongs to capital H. Right? Now we can easily show that this X H X inverse is a subgroup of G. So X H X inverse is a subgroup of G by showing closure property and inverse property. Let H be equal to elements consisting of H1, H2, etc. Hm. Because order of H is equal to M, therefore we can take H is equal to H1, H2, etc. Hm. Now these elements are distinct. So HIs are distinct. That means no two elements are equal. Now therefore X H X inverse will be equal to X H1 X inverse, X H2 X inverse, etc. X H M X inverse. Now we show that these elements are also distinct. For otherwise, suppose X Hi X inverse is equal to X Hj X inverse with I not equal to j. Suppose two elements are equal. What happens? Now by right cancellation law we can cancel out X inverse, and by left cancellation law we can cancel out X. So therefore Hi will be equal to Hj with I not equal to j. This is a contradiction because we assumed that all His are distinct. So this contradiction is because of our assumption X Hi X inverse is equal to X Hj X inverse. So therefore all the elements of X H X inverse are distinct. Now how many elements are there in X H X inverse? So order of X H X inverse will be equal to M. But H is the only subgroup of G having M elements. So therefore X H X inverse must be equal to what? H. And hence H is a normal subgroup of G. Therefore H is a normal subgroup of G. Okay, now let us prove problem number 4, which is, if a cyclic subgroup n of G is normal in G, then every subgroup of n is normal in G. First, let us understand the problem clearly. If n is both normal and also cyclic subgroup of a group G, and if H is a subgroup of n, then H is normal in G. H is normal in G. Okay. Now proof. Let n be both normal and also cyclic subgroup of G. Now let H be a subgroup of n. Since n is cyclic, let A be a generator. A be a generator of n. A be a generator of n. That means what? If x belongs to n, then x can be expressed as some integral power of a, where n belongs to, small n belongs to set of integers, right? Also, since H is a subgroup of n, and since n is cyclic, H is also cyclic, because we have proved this theorem already, which states that every subgroup of a cyclic group is also cyclic. While proving this theorem, we also proved that if m is the least positive integer such that a to the power of m belongs to h, then a power m is a generator of h. That is, every element y belonging to h can be expressed as some integral power of a power m. Right? Okay. Now, what we need to prove? We need to prove for every x belonging to G and h belonging to capital H, G inverse belongs to H. Okay. Now let x belongs to G and h belongs to capital H. Then h will be equal to a to the power of m whole to the power of k, or some k belonging to I. Okay. Now consider x, h x inverse, which is equal to what? X a power m whole power k into x inverse, which can be written as x a power k whole power m x inverse. Now this can be written as x a power k x inverse whole to the power of m. See, this is we have already proved that x a power n into x inverse will be equal to x a x inverse whole to the power of n. So here we can take m outside. So x a power k whole power m can x inverse can be expressed as x a power k x inverse whole power m. Okay. Now, what can you say about x a power k x inverse? This definitely belongs to n. Why? Because a power k definitely belongs to n, because n is cyclic and it is generated by a. So every element of n is of the form a power k with k an integer. And since n is normal, for every x belonging to G and a power k belonging to n, x a power k x inverse definitely belongs to n. Okay, so therefore x a power k x inverse is an element of n. And since n is cyclic and generated by a, x a power k x inverse is equal to some a power p with p belonging to I set of integers. Okay, so now we have from this x h x inverse will be equal to x a power k x inverse whole to the power of m will be equal to, now this x a power k x inverse is what? A power p. So this is a power p whole to the power of m, and that can be written as a power m whole power p, and that definitely belongs to h, because every element of h can be expressed as some integral power of a power m. So therefore a power m whole power p is an element of h. So this implies x h x inverse belongs to h. So we proved that for every x belonging to G and h belonging to capital H, x h x inverse belongs to capital H, and therefore h is normal in G. See, x is an element of G, so therefore h is normal in G. Now next problem number 5. Give an example of a non-abelian group, all of whose subgroups are normal. When we take G equal to plus or minus I, plus or minus 1, plus or minus I, plus or minus j, and plus or minus k under multiplication defined by I square is equal to j square is equal to k square equal to minus 1, and I into j equal to minus j into I, which is equal to k, j into k is equal to minus k into j, which is equal to I, and k into I equal to minus I into j, I into k equal to j. This we can show that it's a group under multiplication and it is non-abelian clearly, because I into j is not equal to j into I. So it is a non-abelian group. And we can also show that every subgroup of G is normal in G. This is a very standard problem. You can take any standard textbook, there you can find this example. Next, problem number 6. If G is a group and H is a subgroup of index 2 in G, then show that H is a normal subgroup of G. Okay, proof. Given H is a subgroup of index 2. So index of H in G will be equal to 2. That means there are only 2 right or left distinct cosets of H in G. Okay. So let X be any element of G. Now, what we need to prove? We need to prove X into H equal to H into X for all X belongs to G. Okay. So there are 2 cases. So now case 1. Suppose X belongs to H. See, X may belongs to H or X may not belongs to H. So this implies H into X will be equal to H, because H is a subgroup of G. If X belongs to H, then H into X will be equal to H, and also X into H is equal to H. So this implies H into X will be equal to X into H, and X belongs to H. Now case 2. Suppose X does not belongs to H, then X into H is not equal to H, and also H into X is not equal to H. Now, since there are only 2 distinct right cosets or left cosets of H in G, now XH and H are the only 2 left cosets, and HX and H are the only 2 distinct right cosets. So therefore, XH union H will be equal to G, and also HX union H is equal to G. Moreover, XH and H are distinct. XH intersection H will be equal to empty, and HX intersection H is also empty. So therefore, from these two, it is clear that XH is equal to HX, and hence H is normal in G. problem number 7, which state problem is, let G be a group of order 2p where p is a prime number, then show that G has a normal subgroup of order p. Normal subgroup of order p. Okay. Proof. Given order of G is equal to 2p, where p is prime. Now 2p is composite order, therefore G has a proper subgroup if it exists. Proper subgroup. Now let H be a subgroup of G. Now what can you say about order of H? Order of H will be equal to either 2 or order of H will be equal to P. These are the only two subgroups if it exists because of Lagrange's theorem. Lagrange's theorem states that if G is finite, then order of H divides order of G. Now order of G here is 2p. The only divisors of 2p are 2 and p. So therefore order of H must be either equal to 2 or p. So therefore there exists a subgroup H of G whose order is p. Now we have to show that H is normal. Now what is index of H in G? Now this is equal to order of G divided by order of H. But what is order of G? 2p. What is order of H? P. So which is equal to 2. So index of H in G is equal to 2. Now by previous problem we showed that if order index of H in G is 2, then H must be normal in G. Therefore H is normal in G. Now last problem in this session. Let Z be the center of a group G. If A belongs to Z, prove that the cyclic subgroup of G generated by A is a normal subgroup of G. Is a normal subgroup of G. Now proof. Z be the center of a group G means what? Center Z is equal to set of all small z belonging to G such that Zx equals xz for all x belonging to G. That means if Z, small z, is an element of capital Z, then it has to commutes with every element of G. So how do we form center of G? Take an element of G and check whether that element of G commutes with all other elements of G. If it commutes with all elements of G, then put it in capital Z. So this is how we form Z. Now Z has one element which is identity element, because identity element definitely commutes with every element of G. Okay. Now given that A belongs to Z, implies Ax equals Xa for all x belonging to G. Now let H be equal to cyclic subgroup generated by A. Cyclic subgroup generated by A. Now we have to prove that H is normal in G. Okay. Now let X belongs to G and H belongs to capital H. Then H will be equal to A power n, where n is any integer. Now consider X H X inverse, which is equal to X A power n X inverse, which is equal to X A X inverse whole to the power of n. And now this is equal to, see here, XA is what? XA is AX. So we can write here in place of XA, AX into X inverse whole power n. Now this is equal to X inverse is E. So therefore this is AE whole power n, which is equal to A power n. Now A power n means it is an integral power of A, and H is generated by A, and therefore this element definitely belongs to H. Hence X H X inverse definitely belongs to capital H. Therefore H is normal in G. So that completes the proof. Thank you.